Let's see if we can't take a look at the conduction system of the heart. Now this is really important because the conduction system of the heart is what basically makes the heart beat. Okay? We generate electricity. Our bodies generate electricity just by virtue of the fact that we're alive. And our heart is flowing, our blood is flowing. When you go in and they do an electroencephalogram, they can detect brain activity, right? Electromyogram, they can detect muscle contractile activity. When we do an electrocardiogram, we can detect cardiac electrical activity. It's that electrical activity that really helps us to determine whether or not the heart is healthy and if it's beating properly. And to understand how this electrical activity actually works, we have to understand the pathway, okay? So at the right atrium level, we have what we call the SA node. Okay, so the SA node stands for the sinoatrial node. Sinoatrial node. And this is also called the pacemaker of the heart. Again, I will pose the question to you. What is a normal heart rate? 60 to what? 60 to 100. Therefore, the SA node is always going to be in control of beating the heart between 60 and 100 beats per minute. The SA node is really important. The next node we'll find right here at the base between the right atrium and the right ventricle. This is called the AV node or the atrioventricular node. This node is still very important, but it beats the heart between 40 and 60 beats per minute. Okay? 40 and 60. Now, once we go from the atrium, because obviously when the heart beats, it's not one chamber at a time. It's atria, boom, ventricles, boom, atria, boom, ventricles, okay? So from the SA node to the AV node, we get into now the ventricles, right? And in the ventricles, we have what we call the bundle of His. Okay, and I'm going to write this down separately over here so you can kind of follow me. So the bundle of His actually is responsible for the heart rate between 20 and 40. Well, 20 is not enough to sustain life. If your heart's beating 20 beats per minute, you're going to be on the ground. You don't have enough. You can't 20 beats per minute. You don't generate enough pressure to be able to push the blood to the brain and the rest of the body. That's something. God bless you. That's something we'd have to put the person cardioversion for to get it up a little bit if we can get it beating. So we have the sinoatrial node. We have the atrioventricular node. We have the bundle of His. And this is not coming in very clear. So sinoatrial node, S-I-N-O-A-T-R-I-A-L, atrioventricular, and bundle of His. Okay, now the bundle of His, from the bundle of His, there are what we call bundle branches throughout the entire heart. Typically, a lot of these are in the myocardium, right? You've got the layers of the heart. What are the layers of the heart? You have the outer pericardial sac, or the pericardium. Then you have the epicardium, which is outer, myocardium, which is inner, endocardium, which is most inner. The myocardial activity is where you'll find a lot of this electrical activity going on with bundle of His and Purkinje fibers and, bundle branches, electrical signals that are being, transmitted hither and from. So the bundle of His, then we have bundle branches and the Purkinje fibers. Now these guys are all responsible for translating the electrical activity all through the heart and back to where the sinoatrial node is. Now what's the most important part of a heart for a heart to be healthy? It has to beat, it has to rest. It has to beat, it has to rest. When a heart rests, what happens? The coronary arteries all fill up with freshly oxygenated blood, and the heart is perfused with fresh blood that allows it to continue its process daily. Okay? So, how does this work? Well, basically, the SA node sends electrical signal and the AV node picks it up. Remember, electrons travel, don't they?
Yeah.
If electrons aren't directed, they're everywhere. You can find electrons in the air. You can find electrons everywhere. But to be able to use electrons, you have to direct them, right? Usually from negative to positive. So basically the electron flow is such that the SA node is going to send electrons to the AV node. The AV node is going to send more electrons to the bundle of His. The bundle of His is going to send electrons to the bundle branches that are throughout the heart. And then of course bundle branches are going to send electrons to the Purkinje fibers. The Purkinje fibers line the heart. They're all over the place. I like to think of this as baseball. This makes more sense when you think. Anyone baseball fans here? Couple, few baseball fans? Okay. So baseball, you've got the batter. Okay? The batter hits the ball. It goes to, maybe the catcher catches it. Let's say the catcher catches it. It's not an automatic out though, okay? It's not an automatic out. We're going to go from there. Oh, maybe he catches it, but he throws it to somebody on first base. First base would be the bundle of His. Then the bundle of His, the guy at first base is going to throw it to maybe second base or third base, to the bundle branches. And the bundle branches are going to throw it to the outfielder, which is the Purkinje fibers of baseball. However, you have to understand it. You need to know the different electronic or electrical where the receptors are, where electron receptors are, and where the charges are deposited. So when we look at the flow, we see that electrons will eventually come back to the SA node, and immediately when the SA node is bombarded by electrical activity, we call it depolarization. And we're going to look at this translation in actual real time, in simulation, on how this translates into an electrical rhythm of the heart. So let me just go ahead and erase the heart for a second here. And we're going to try to put this together. And this is all online, this is all in the reading, so if you need to verify, you can take a look.
Yes, I do have a question.
Yes, please.
About the, this is actually one of the questions on the test.
Okay, what is the question?
It's weird, because it said the electrical conduction of the heart follows which of the following path. I put the SA node, AV node, bundle of His, Purkinje fibers.
And that's fine, and that's fine, because bundle branches and Purkinje fibers can be interchanged. At any one time frame, there's give and take between the two.
Okay.
So you're fine with that. I get questions from other students on that particular question as well, but that's absolutely fine. So the SA node gets hit with electrons, it depolarizes to from negative 60 to negative 90 electron volts. It depolarizes. And we continue through the AV node to the bundle of His, to bundle branches, to Purkinje fibers, And once we get to the Purkinje fibers, basically the heartbeat's almost over. Boom, boom. That's your lub dub. When you had the opportunity yesterday to go to clinicals and assess your patients, when you listened to a heartbeat, you heard, right? That was the heartbeat. It's different than feeling a pulse, isn't it?
Yeah.
When you listen to the heartbeat, you hear the lub dub. That's counted as 1. 1, 2, 3. That's the heartbeat that you're hearing. So this heartbeat is generated by the electrical impulses that are transmitted through these different electrical receptors. Okay? Stop me if you have a question. Okay, so when the heartbeat is almost finished, lub dub, there's a time that we call repolarization. So repolarization takes place generally right at the end of the Purkinje fibers transmission. Yes?
So
I-
AV stands for 4 in the body, left, right, top, bottom, right?
Correct.
Okay.
Yeah, there's 4 chambers of the heart. 4 chambers of the heart. However, what you need to understand is even in the 4 chambers of the heart, electrical activity is firing through all the chambers. But the SA node, the sinoatrial node, is in the right atrium. And the AV node is still right in the right atrium by the right ventricle. That's why we call it the atrioventricular node. Because it hasn't completely crossed into the ventricles, but it's there. That's where it's located, okay? So now what we're going to look at, if you've written this down, I'm going to show you something. Any other questions? Questions? Okay, so let's take a look at what a heartbeat looks like, okay? I'm going to try to make this bigger. There's a heartbeat. Lub dub. Bless you. Lub dub. So what are we looking at? Well, basically, we're looking at a P wave. Okay? So to have a P wave, we have to know what normal is before we can diagnose abnormal, correct? You have to know what the norm is. You have to know what the baseline is. What does a normal heart rate look like? Well, typically there's a P wave, there's a Q wave, there's an R, there's an S, and there's a T. Okay? Now, how does this translate into the electrical nodes that we just looked at? Well, the reason we look for P waves is because P waves signify a sinus rhythm, which means it's originating in the sinoatrial node. So depolarization, for depolarization to occur, or if it does occur, is going to generate a P wave. So this is where depolarization takes place. This is where the SA node gets all fired up and starts to transmit electrical activity throughout the heart, so the heart beats. So from P, we go to Q, so you're going to look at Q as the AV node. Okay? So this is SA node, AV node, all the way up here, and now we're going to get into ventricular activity from this side over. AV node, we have bundle of his coming down to the S. We've got bundle branches. And then up going through the T, we've got the Purkinje fibers. Now, let's look what happens. This line right here is coming down, and it's flattening out, is it not?
Yeah.
Okay, this is called, when it flattens out and becomes one with the horizontal or x-axis, we call this the isoelectric line. This horizontal axis that the rhythm is translated upon is called the isoelectric line. Isoelectric line. We have to come to 0 for the heart to rest. Right? We have to come to 0 for the heart to rest. So right here, where you can draw a tangent line with the slope of this curve, right? A tangent line connects a curve at one point. That's how we define tangent, right? This is where repolarization starts to take place. The heart starts to repolarize, starting to get fired up again as it's going through its resting phase. This has to rest so that the heart can refill and perfuse itself with what? Freshly oxygenated blood throughout the coronary arteries. That makes sense? Following me? So when a person goes in for an echocardiogram, we look at what we call ejection fraction. And typically ejection fraction can be 55 to 70% normal. Below that, below 55, we start to think about possibly there may be some perfusion problems. We can actually determine perfusion problems by looking at an lead tracing. But of course, you're only looking at, basically like leads 1 through 6. You're not really looking at the whole heart in its entirety. And if we wanted to look at the heart posteriorly, we'd actually have to put leads in the back. But we're not doing that. Basically, we're looking at the full frontal part of the heart, the anterior and the lateral parts of the heart. So it's kind of hard to diagnose a posterior MI, without actual posterior lead placements in the back. But you're not going to be doing that, okay? So this is basically how we look at a heart rhythm. Now the other thing is, what you need to know is if this is translated on a piece of graph paper or EKG lead paper, we're going to count because there's normal distances. This is how we determine whether or not a rhythm is normal or abnormal, by the distances between the different labels that we have here, okay? And we've plotted, and it's been accepted in literature, that there are normal variations for each of the distances. So the distances that I'm going to show you are your PR interval. Some people say PRI. A normal PR interval is between 0.12 seconds to 0.20 seconds. We're going to look at the QRS interval, and I'll show you what this is, which is usually between 0.08 to 0.12 seconds. We're going to look at the QT interval, which is typically 0.34, 0.36 to 0.44 seconds. And you almost have to memorize these to be able to determine whether or not you have a normal rhythm or not. First thing we're always going to look for to know that it's a sinus rhythm is a P wave, right? It's got to have a P wave. Yeah, question. Oh, sorry, I'm in the way. I apologize. Go right ahead. And so I'm going to show you how to measure these. It might, if you like this stuff, you might want to get yourself some calipers. Calipers are cool. Remember when you guys were small and you took geometry? Remember the compass, right? Or protractor. I think it was a protractor, wasn't it? Yeah, the protractor. How you could measure things. It had those two sharp little things, and you put a pencil in it. That's what calipers look like. They look like the same thing. But you always measure on the horizontal. See, that's the thing. You have to measure on the horizontal. You can't measure. We don't want you to measure angles and things like that. The distances are always going to be measured on the horizontal line. The x-axis is always going to be in time, right? It's our independent variable. You know that from statistics and economics. X-axis is time. It is an independent variable. Y-axis is in electrical voltage, and this is a dependent variable. dependent variable. Okay? Not that that's, really going to help you too much, but you know your X and Y's, okay? You always have to measure horizontally with your calipers, okay? Okay, so this is what we've got. How do we measure? Well, basically this is how we measure. We kind of take our calipers. I'm going to use 2 pens because they kind of look like a caliper. And when I measure PR, I'm going to measure from the peak of the P to the peak of the R. Literature doesn't say that, but it's much easier for me. I like to measure that way. It just makes more sense. What I do is this. I drop a perpendicular from the peak of the P, and I'll drop a perpendicular from the apex of the R. Now I can see it. Now I'm not guessing. Where's the curve? Where's this? Where do I start? Where do I end? That's just waste of mental energy. No, drop your perpendicular from the apex to the highest point, where you can again draw a tangent line to the point, right? And measure the distance. Oh, there's my distance. Take your calipers and measure. Now your distance should fall between zero. If it's a PR interval that falls within the normal range between 0.12 and 0.20 seconds, you should get a value. Now I'm going to show you what we mean by seconds on the horizontal in a minute, okay? But first I need to show you how to measure. You would take your calipers again to measure QRS. How do we measure QRS? Well, basically I look at the distance between the Q and the S coming down, right, sloping downward, and I measure the distance this way. It's kind of hard because the Q doesn't drop this far. So if you wanted to drop kind of 2 lines coming this way, you could. I usually come at the peak of the P or the Q and just measure to the R. There's my distance. The QRS should be between 0.08 and 0.12 seconds, right? If it's normal. I'm just showing you how to measure right now. QRS, QT. Now, when you measure the QT, you're going to measure from the Q, and you see this tangent line right here? Intersect it with a perpendicular, and you're going to measure from the Q to the T. Okay? Q to the T. So it's where the T slopes downward but doesn't completely touch. Yes?
So how come we got the measurement from the peak of the P and not the peak of the T?
Because we're looking at where the heart is going to get ready to repolarize.
Okay,
That's where we're taking it to.
okay.
But that's a really good question. She asked why don't we measure it from the perpendicular line drop from the T, because the T's not finished doing what it's supposed to do.
Me too, until it hits the
Right.
the
Correct.
final point.
Yep.
Okay.
All right, so now what we're going to do is I'm going to show you a grid, and then we're going to take a look at some diagrams here. Give you a grid here. So basically, when you look at EKG paper, it kind of looks, one box looks like this. Let's see, let's do it this way. 1, 2, 3, 5, 1, 2, 1, 2, 3, 4. Okay, this is considered one box. This is one tiny little box on an EKG paper. And each of these, okay, we're measuring in the horizontal, are spaced as follows. Each of these are 0.04 seconds. 0.04, 0.04, 0.04, 0.04, 0.04. So the total of one box, if we were to add up 0.04 5 times, would be a distance of 0.20. Am I correct?
Yeah.
Follow me so far? 0.20. If we're measuring on the horizontal, if we're measuring in the vertical, which we don't typically do as telemetry technicians because typically the vertical and the horizontal are related in almost a 1-to-1 ratio. Most of the time, you do want to inspect height in certain cases where it seems totally off the map. But these are measured in 0.1 electron volts. So 0.1, 0.2, 0.3, 0.4, 0.5, etc., etc., etc. So each of these boxes are stacked on a piece of paper. They're all over the place. And what happens is the heart rate is translated onto the grid, and because we know the distance of each of the grid squares, we can measure the horizontals. Yeah? Good?
Yeah.
So what we're going to look at in the next few minutes is we're going to look at rhythms, and I'm going to explain to you why these rhythms are normal or abnormal, okay? So look at this. If you measured your PR and it's between 0.12 and 0.20, you measured your QRS, it's between 0.08 and 0.12. You measured your QT between 0.34 and 0.44. We're kind of beginning to look at a normal sinus rhythm then, right? A normal rhythm. As long as the heart rate is what? Between what? 60 to 100. So if our heart rate is between 60 to 100, we're good. We're groovy because that means we've got a good solid normal sinus rhythm. Nothing's out of place. Everything measures correctly. There's a P wave for every QRS and a QRS, right, for every P wave. Excuse me.